All right, folks, good morning. Coming to you from beautiful Palm Springs here. Hope you're doing well. Sorry I couldn't be there, but I'm flying back tonight. Flights were just a lot cheaper. So I recorded this video for you. We're going to learn a little bit something new. Really good lesson. Sorry I'm missing this one. Hopefully you're being nice to your sub. But without further ado, let's jump into it so we can get talking about this. All right, we have talked about this a little bit, but we are going to be working on fitting. Go away. Sorry, this stupid Zoom. Now we're going to finally talk about curved relationships. So we're going to do different regressions. We've only done linear regressions. Now we're going to do some other regressions, and this is 2.8. You want to write that down? This is 2.8. All right. So there is that. Sorry, I'm still moving some stuff around here. All right. So there are cases where we want to use a quadratic model to fit a nonlinear association between two quantitative variables. So if we don't want to use a linear model, we can use a quadratic model. Here is the quadratic model, right? We're going to write it as y equals ax squared plus bx plus c. And it makes a parabola, okay? Very famous. You guys have done this stuff. Hopefully since you were in Algebra 1, where you did some quadratic stuff. So now we're just going to work on fitting some quadratic models to a parabola. We're, again, mostly going to use our calculators here, so keep bringing your calculators for homework, for tests and quizzes. And we probably will have a chapter 2 test at some point. We will, when I come back on Wednesday, we're going to do an in-class project, which is we're going to work on these fitting models to the relationships to see if we can find anything interesting. And then probably a review day, and then maybe a test after that. So not this week, but probably next week we might have a test. Maybe we do another project day, but we can see how it goes. Okay, so here we go. Let's take a look at an example here. Okay, so here we go. We got some data. What do we got here? So income is our explanatory variable, right? So we got income here. This data is probably a little old with those $10,000 isn't that much, but it could be from somewhere that they don't have that much money. We don't know where this data is from. And then test scores, right? And again, you could fit a linear equation and it kind of get there. It would kind of be there, but it's best if it fits curved, right? At some point, you're not going to be able to get higher test scores, right? No matter how much money you have, there's going to be a maximum test score that you can get. And so that's where this quadratic relationship, this curve relationship, makes a lot of sense. So if we have stuff that has like a limit or a maximum, or we're just increasing at a rate that is higher, we want to use our quadratic regression instead of a linear. Okay, and a linear might explain it well for some of the data that's, you know, around here from the 10 to 20,000, but when you get further up, it doesn't explain it well. Okay, so let's do an example. And again, we're going to go back and forth between this and the calculator here. So I might need a piece of paper. Okay, so table below shows the speed and the distance needed to come to a complete stop. So we have speed in miles per hour and we have distance. And yeah, there we go. So we're gonna do a little calculator. So pull out your calculator. I am actually going to pause this and whatever. Actually, sorry, let's go back. Okay, pause it now and put this data in your calculator. I'm going to do the same thing. And then we'll come back together and take a look at the graph. Okay? All right. All right, so here we go. We're back in it. Hopefully you put your data in your calculator and it looks something like this, right? Now, one thing we want to do before we do anything else is you probably have your residual plot on, and right now we don't want that. So let's remind you, and we're going to go second y equals. Your plot probably says L1 resid. We want to put it back to L2. So we're going to go back down here to residual, and we're going to hit second stat, and it's going to bring up our list, and now we're going to put it back to L2. Okay. So now if you go zoom 9, you should just see the data and not the residual plot. Okay. So that is our data. Look at what it looks like, kind of curving upwards. All right. So there's that. That would be our plot. Now let's fit the line. Okay. So now we're going to go stat, calc. We've been doing 8, which is a linear regression, but now we want to do a quadratic regression. So we're going to go down to number 5 and we'll pick quadratic. We're going to look L1, L2, and then if you want to store it in the y equals, remember we can go vars, y vars, function y1. Okay. Now it's going to calculate, and it's going to give us the equation, right? So it gives us this equation 0.04 x squared plus 0.33x plus negative 2.29. Okay, that's our equation. And then look at what they give us at the bottom. They give us an r squared, okay? We don't get a correlation value, but we get an r squared, which again tells us how accurate our predictions would be and how good the fit is. Look at this fit. It's almost perfect, right? And that's because we're talking about physics here, right? This is like a real equation, and we're talking about physics, okay? So now go zoom 9 again, and if you put that equation in, look at that, there you go, right? So we got one point that's maybe right above it, but like all the other points are right on the line, okay? So there we go. That's how you run your quadratic regression, and you put it in your calculators, and we got the quadratic regression up. If you missed any of that, just go back and rewatch what I just did and try to fix it. If you're having trouble with your calculators, just ask a neighbor or something. Sorry, I'm not there to help with the calculators, but that is the quadratic regression. All right, let's see if there's anything else in this. Why are you freaking out, son? Go away. All right, so let's just move on there, and we'll do an exponential model. Okay, so exponential model, hopefully you can see that. Sometimes that stupid thing is blocking. So for our exponential model, it's y equals a times b to the x. Sorry, I haven't written on Zoom in a while. That's an x. That's a multiplication. Okay, so we got our starting value a. B has to be greater than 0, and it's b to the x. X is our variable. Hopefully that wasn't too blocked by my picture there, but maybe it is. So there's that. If b, yeah. So this is just exponential growth model. Again, hopefully you've seen this stuff before, but we'll practice it if you haven't. So b is greater than the 1, or we're going to get exponential growth. Okay, and again, this stuff, quadratics, which we just did. We just did quadratics. Quadratics come up in physics. They come up in well, they come up in a lot of science, and a lot of it's physics, how gravity works, right? So quadratics come up a lot. Exponential growth and decay come up a lot. So exponential growth, right? Population stuff is exponential growth. Finance stuff is exponential growth. There's so much exponential growth stuff, which is cool. And then we also have exponential decay. So if you know b is between 0 and 1, we have exponential decay. And that also shows up in science, shows up in chemistry, right? Nuclear decay, right? Something that is radioactive decay, that's what it's called. If you have something that's a radioactive isotope or something and it's shooting off little bits of itself, it's going to exponentially decay. All right, so we have those two things we're going to deal with. Again, lots of real world examples here, so hopefully that is interesting to you. Let's take a look at an example. I don't know what any of this data is, but you can see we kind of have exponential decay here. Okay, so we got an exponential function. It's going out like this. And that is something we'd want to fit an exponential regression to. Okay, so let's see. I'm sure we're just going to jump into an example here. Ooh, again, this is like real stuff, folks. This is a huge example, and this is true. So Gordon Moore in 1965, I think he was working at Intel, said that the number of transistors in an integrated chip would double every 18 months. This is called Moore's Law, and it's held true. He predicted this in 1965. Every 18 months, our chips get that much better. That's why computing has gotten so much better since 1965. And it's Moore's Law. So super interesting stuff here. Here is the data. So years since 1970, number of transistors. And here we go. There's all the data. Hopefully you can see that. So again, pause it now, put this data in your calculator, and let's come back together and we will take a look at it together, huh? So go ahead and pause, and I'm going to pause as well. All right, so hopefully you put that in your calculator, right? Should look something like that in the old calculadora. And again, make sure your stat plot's on L1, L2, and let's just take a look at we should clear this, clear your quadratic function. And then let's just go zoom 9 and just take a look at the data. Woo-hoo-hoo-hoo-hoo. That is definitely exponential, right? Look at that. Boom. Okay, so now let's do the regression line. So we're going to go stat, calc. So last one we did 5 was quadratic regression. Then we've done 8 a lot for linear regression. And now I think we got to go down to 0. Yeah, go down to 0. It's exponential regression. We're going to enter L1, L2, and we can store it like we've been doing. So we're going to go vars, y vars, function, y1. We're going to store it in y1, calculate. So here's our equation, right? Our equation, I don't know why I can't talk. Y equals 1.88 times B, okay, which is 1.38 to the X. That's our equation. You can see we do get an R value in this one. So we get a correlation, highly correlated, as we would expect, because this is basically an equation itself. This guy came up with this thing that it's going to double every 18 months. So that's why you don't see it exactly being a doubling here, because it's every 18 months, not 1 year. And then our R squared is very high. So this regression is really accurate. It's very good. And if you go zoom 9 again, we should see it, and it's right on. Well, actually, it's a little, this one's a little bit off. So it is a little bit off in a couple of spots, but it would be interesting to get one more point and see how it's doing. But there you go. That is that's our exponential regression, Moore's Law, super important law. So all good there. Let's jump back over to the notes. And I think we probably just have one more slide. Okay. So now maybe I'll just leave it like this. Maybe I won't block the thing then. So here's the most important part. Now we have 3 regression models, right? We got linear, exponential, quadratic. And sometimes it's hard to tell which one would best fit our data, right? We've looked at very clear examples today. We looked at a physics problem with a car trying to stop under braking. We looked at Moore's Law. Those were really clear. But we're going to get real life examples, of course, that might not be so clear. So how do we tell, should we use linear, quadratic, or exponential? There are 2 ways we can check to see which model is better. Way number 1, okay? Our quadratic model only gives us an R squared. We don't get an R value with it. So we want to compare the R squareds between all 3 models and pick the model with the highest R squared. So you're gonna run all 3 regressions. You're gonna put that data in, you're gonna run linear regression, quadratic regression, exponential regression, and then write down the R-squared values. And our best regression will probably be, not necessarily, but will probably be the one with the highest R-squared value. So you can do it that way. Secondly, we want to check the residual plots. So we could check all three residual plots and make sure the one that we pick looks the most random, right? We talked about that last class. Our residual plots are how random the data looks, right? The more random for the residual plot, the better. Let's see. Hopefully we have one more example here. I'd like to see one more example to show you this. Let me see if I can find a good example. We'll do one more example, okay? And then we'll be done. All right, let's look at one more example. So here's some new data. So take a minute if you need to pause, put this in your calculator, put this data in, and then let's go through it together. So pause it, put this in, let's do it. Okay, so now, again, let's get rid of our y equals, and let's just go zoom 9. Here's our data. We might already have an idea what you think, but let's just run through the regressions and see, right? So we're going to go stat. We're going to go calc. We're not going to store any of it this time because let's just not. So we're going to go 8. Check that out. 8 is linear regression first. Okay, we get this. Okay, we get an R value. Remember, we're not going to look at the R value, but we get an R squared value of 0.87. So linear, we got 0.87. Okay, and then let's keep going. Sorry, that's terrible. Well, let's do the other one, stat, calc. We're going to do quadratic. That's number 5. Go down, calculate. It gives us an R squared of 1. That's as high as you can get. I know this data wasn't interesting. Sorry, I had trouble finding a good example. So our quadratic is 1. That's about as good as it gets, but let's check exponential just in case. We're going to go stat, calc. It's all the way down at 0. There it is. Calculate. Ooh, didn't like it. Oh, because we had, yeah, that's my fault. So this one didn't work because I picked bad data. And yeah, we had a 0 in there at some point, right? B was 0 at some point. So that one didn't work. Bad example by me, but you get what I mean. We compare these two, right? We get 0.87 and 1. And then if we do want to put the line on there, we can check it. We can do 5. Let's put the line on. Function y1, we'll put the y in there. And then if we zoom 9 it, there's our data. And you can see it's perfectly quadratic. I picked a bad example. I'm sorry. I was just trying to find something. But you could see that one worked, and linear would have been okay, but not as good, right? And if we really want to, we can check the residual plots. We can go second stat plot. This one isn't going to look good, though. It's a bad example. Okay, let's leave it. We'll do it when I get back and look at some residual plots because this one's a bad example. But anyways, that's how you could compare them. You're going to get a little homework assignment now. It's on Google Classroom, so please make sure you complete the homework assignment. Practice this stuff. Just get it done in class, folks. You got plenty of time. And I'll see you on Wednesday. Hope you have a great day.